Right, so I just want to cover a few important points from limits and continuity. So, I'm giving you guys a little assignment from the book with some problems that are similar to the problems that I'm going to do right now. Not sure I'm going to be able to keep this video to 15 minutes, which is usually my goal, because I'm doing about 5 problems, something like that. No, 6. Okay. So first, use a table. We're going to need a calculator for this. And you've learned a different way of doing this problem already, but when this shows up in the textbook, it hasn't been taught yet. So we're going to follow the instructions, and then I'm going to show you the different way. So first thing that's important here is, in order for the general limit to exist, we need the left-hand limit to equal the right-hand limit. So that means I need to approach 3 from the left and also from the right. Not sure why I did one more there than I did over here, but whatever. We probably don't need this many values to see what's happening with the pattern in the y values. So the limit is talking about x getting really close to one value, and the y is going to get close to another value if the limit exists. So here's what I'm going to do. I'm going to put the function in my y equals. You're also probably hearing my daughter's teacher teaching right now too, so that's fun. Dual lesson. All right, let me make sure I typed that in correctly. Okay, and then I'm going to go to my table. Remember, see, I need to do my table set. I need to set my independent to ask. My independent is my x value. I want the graphing calculator to ask me for the x value. So I can type in, yeah, we definitely don't need this many x values. And see, the table only goes to 4 decimal places, so it can't even show me the value. So I'm just going to get rid of this because I don't want to put 2. It's not 2. I could figure out the pattern. It's 2.03, 2.003, 2.003, so this would be 2.00003. Hopefully you see that pattern, but to show the work on this, we would do that, and then I'm going to go from the other direction, and I bet it would be the same thing if I did, yeah, see? So I'm going to get rid of that. I don't need that. The only reason to go further on the x is if the pattern in the y wasn't incredibly clear, but this pattern is very clear. And this would actually be a 6, 7 here if the calculator could go to further decimal places. You can see that that pattern is happening there. Excuse me. So now what I want to really show you is this table is indicating that the limit as x approaches 3 from the left is equal to 2. This table is showing that as x approaches 3 from the right is equal to 2. Since the left-hand limit does equal the right-hand limit, then the general limit, I'm going to write it out this time, is the same value, 2. So the answer to this question is 2. Now, that would be if it following directions. This problem we can actually solve a different way. You learned how to solve these algebraically. Okay, so one thing you need to be careful of on the AP exam, don't get lazy and drop your notation. A lot of times people are like, I don't want to write the limit, I'm feeling lazy, I'm just going to write that. And then they all of a sudden add a limit in there. They're working out these problems and there's no limit and then there's a limit and it just doesn't make any sense. So be careful of that, okay? Write the whole problem, don't be lazy. If we solve algebraically, which one of the methods was factoring, We can cancel out the factor that caused there to be a 0 in the bottom, right? We don't want to have a 0 in the bottom. And then plug in DSP, direct substitution property, DSP. Plugging in gives me 3 plus 3 over 3, which is 6 over 3, which is 2. Obviously, that's an easier way. So we would only use tables like this if we couldn't solve algebraically. Okay, you're not going to be required to solve using tables when there is an easier way. It's just not how it works. Okay, next page. I'm going to assign problems similar to these. Let's see. We're going to evaluate algebraically. I kind of actually just reviewed that. Maybe I'm going to skip this one because I kind of just reviewed that, didn't I? So I'm going to skip this one. We're going to do fewer problems that way. All right. So algebraically was the factoring to cancel out. So notice if I plug a 3 in right off the bat, if I use the direct substitution process property right off the bat, I get a 0 in the bottom. And I don't want to have undefined as an answer. So that's when I know I need to do something else, which oftentimes is algebraic, but sometimes results in needing to have a table. Okay? So always check DSP first. All right. I think they're having a dance party on their Zoom call. How fun is that? We should have a dance party one day. Oh, they're singing happy birthday. Is this really what I wanted to do here? I feel like this was super easy. Okay, I don't know why I said I was going to do this problem. Okay, so maybe we can use this as a little review though. Is this function continuous at x equals -6 or c equals -6? Well, we can use DSP. Sorry, that's like super distracting for me. I hope it's not as distracting for you as it is for me. This is undefined. Since it's undefined, remember there's 3 pieces to continuity. I'm going to review those in the next example, but one of them is that the function has to be defined at that value, and this function is undefined. So the answer is no, it's not continuous. And we know from knowing how to graph these things that there is an infinite discontinuity. There's an asymptote at x equals -6. Okay, that was easier than I remembered. I don't know why I picked that one. Let's do a different one. Alright, so same directions. Determine whether f is continuous. This time we're getting a piecewise function. Oh my god. I don't know how much of that you can hear. This was not my best idea to try and multitask right now, but it's fun, right? All right. There's 3 things to continuity. One of them is that the limit exists. In order for the limit to exist, the left-hand limit has to equal the right-hand limit. Okay? So we're going to check the limit. I didn't write down the c value. The c value is c equals 1 for this problem. So they want to know, is this function continuous at c equals 1? Okay, that was given. So the limit from the left would be for the less than. So I want to find the limit as x approaches 1 from the left. And I'm going to use that piece. And here's another review. I'm glad I didn't do that algebraic problem. Here's another review of algebraic evaluation. If I plug in a 1, I get a 0 in the bottom, so DSP right off the bat doesn't help me. So then I need to factor. If you don't remember how to factor difference of cubes, you need to look that up, please. Same, opposite, always positive. And we can cancel out now. This was the problem child that made the denominator equal to 0. So now we can do DSP again. Let's actually write up here what we did. No bueno, right? Okay, now we can do DSP again. Plugging in the 1, we get 1 plus 1 plus 1 over 1 plus 1. So 3 over 2 is the left-hand limit. The right-hand limit, we're going to use the greater than piece. So we're going to go 3 over x plus 1, and we're going to check DSP always first, because sometimes, ta-da, sometimes it just works. We get 3 over 2, left-hand limit equals right-hand limit, so we're good here. Requirement number 1 works. The limit exists. The limit value from, I'm trying to figure out where to write this to conserve space. From this, we can say that the limit as x approaches 1 of this function is equal to 3 over 2. Okay? Now, the second thing is function is defined. Is the function defined at x equals 1? Yeah, it tells me right here. When x equals 1, the function value is 2. F of 1 equals 2. We're good there. Third requirement is that the limit equals the function value. The limit we said was 3 over 2. The function value was 2. Those are not equal. We failed that test. That means that this function is not continuous when x equals 1. And what that would look like is, I'm not even going to try and draw it nicely. The limit exists and is 3 over 2, but the function value is different. So that's going to be a removable discontinuity. Whitney, stay over here, please. Don't go back there. Okay, 2 more. I don't want you to go back there at all, okay? Please, just stay here for a little bit. Yeah, I hope you guys are going to watch the Thunderbirds too. Okay, let me finish this, please.
Is that 150?
Yes, I know. I'll post this, and maybe if you watch it, you'll see, and you'll know to go see the Thunderbirds. You probably already know, though. Okay. So here's my piecewise function, and I want to know if it's continuous when x equals 0, or C is how the book writes it. Okay? I'm going to go through the same process that I just did. First, I'm going to check if the limit exists. So the left-hand limit, I'm going to use the less than. So I'm going to use 2e to the x. I'm going to try DSP because I always try DSP first. When I plug in a 0, e to the 0 is 1. So that's 2 times 1. For the right-hand limit, I'm going to use the greater than piece. And yet another example of simplifying algebraically. So I'm going to take out an x squared and cancel it with the bottom. If you need to see that work, please do that work, okay? Take out an x squared and cancel it with the bottom. And DSP, direct substitution property, I get a 2. So the left-hand limit equals the right-hand limit, means the limit exists. So we're good there. And I'm going to write it out so that it's easier for me later. The limit is equal to 2. Okay. Second, I need to see, is the function defined? Does f of 0 exist? Yeah, f of 0 is 2. Tells me right here, when x equals 0, y equals 2. Third is, does the limit equal the function value? Well, the limit was 2 and the function value was 2, so we met that requirement this time. So the answer is yes, the function is continuous when c equals 0. Okay, I passed the 15-minute mark, but I've got one left. All right, and I think this is going to be the fastest one. I'm just checking to make sure I'm doing everything I wanted to do. Okay. Sweetie, can I finish this, please? So we're checking for continuity when x equals 0. That's what this is telling me here. Because remember, the directions said determine whether f is continuous at that given c value. So going through the process yet again. I'm not going to write out everything out this time. I'm going to check the limit from the left. I'm going to use the less than piece. I'm going to use DSP, and I get 0 over 0. I guess I didn't show that up there, did I? So that's no bueno. We don't want 0 over 0. So we're going to factor. I'm going to factor out an x from the top and an x from the bottom and cancel it. And then I'm going to do DSP again, and I get negative 6 over 6, which is negative 1. Then I'm going to calculate the right-hand limit using the greater than piece, because greater than is to the right, yeah. I'm going to try DSP, and oops, why did I write an equal sign twice? I get 1/2. So I don't need to do any algebraic methods or anything like that, okay? Sometimes DSP works in that very first step. Left-hand limit does not equal right-hand limit. Therefore, the limit does not exist. That's the first requirement of continuity. Therefore, it is not continuous. Okay? All right, I hope that that really drove home some of the concepts of the limit. So continuity is one of the more heavily covered topics on the AP exam next year. So that's why I really want to drive home that there's 3 pieces, and every time you check for continuity, you have to use the definition of continuity, which is these 3 pieces. Don't tell me I can draw the graph without picking up the pencil. Don't tell me that there's a hole or an asymptote. You have to use these 3 pieces if it asks you to check for continuity. And then just one more thing I meant to find a problem that would discuss this, but I decided that they were all too easy. So let me the idea of a limit is not what happens at that x value. It's what happens when we get very close to that x value. So for example, if I'm talking about the limit as x approaches 2, I'm not asking you what's the function value when x equals 2. The answer to that question would be 1. What I'm asking is if I get very close from the left and the right, what is the y value getting close to? Okay, the y value is getting close to 2. So in this case, the limit is 2, but the function value is 1. The limit is different from the function value, okay? In this case, the limit as x approaches 2 and the function value are the same because this graph is continuous, okay? And then I kind of hit this already, but the limit does not exist at x equals 3 because the left-hand limit does not equal the right-hand limit, okay? Hope that helps clarify some stuff, and if you watch this before it's due, have a good weekend.